All right, everybody, my name is Scott Burke. I'm going to be the reporter for the Rankine cycle experiment we did last class. All right, so a little bit of theory and experiment synopsis is the whole idea behind this experiment is learning how a turbine can actually generate electricity, hence the light bulbs that are gold and purple. So it's showing how steam goes through a turbine and actually makes electricity through the electromagnetic field generated with the stator coils and the electromagnets turning. Laws of thermo that apply to this lab are the zeroth law, which allows us to measure temperature. This means if one thing is a certain temperature and another thing is a certain temperature, and there's a third object that's in equilibrium with one of them, then it also has to be in equilibrium with the other. So if you have a thermometer and it's in equilibrium with something in there, you can actually measure the temperature. The first law allows us to determine power, heat input, and output. That's basically based off the conservation of energy. The second law allows us to calculate the efficiency of the turbine. It gives us an ideal standard for comparison that talks about the generation of entropy. Things have to become more chaotic. And we will use the Rankine cycle heat engine to power generator and electric lights and things. So here's a little bit of the raw data. So we just read this off of electronic temperature gauges. So that's in Fahrenheit. The PSI was all the pressure gauges back there. That's actually in gauge, so we had to add 14.7 PSI, which is roughly 1 atmosphere, to get it up to absolute. So this is actually what's going on in here. So it's actually supposed to be isentropic expansion through the pump right here, or compression, through the pump. And then it goes through the vaporizer, which is kind of like the same thing as the boiler. But that's actually over there in Cogen plant, like on the other side of campus. So that's the boiler they have there. Also the pumps on that side of campus. It goes through the expander, which is the little tiny turbine we have over there. And that's also supposed to be isentropic, but this is the actual 4S is the ideal. And then it will go back through the condenser to actually turn into water so they can pump it back to where it came from. And here's the values I measured here and tabulated values for the intermediate. So I assume steady state, steady flow, even though it probably wasn't exactly that. It changes a little bit, but I just assumed that to kind of do some things. The volumetric flow rate was actually through the condenser, but that's 8 gallons per minute. And the density of water, I just said it was about 1,000 kilograms per meter squared for the liquid water. And that yields a mass flow rate of 0.0254 kilograms per second. And the pump power can be calculated using this formula right here, which is, that's actually the specific mass times the pressure difference times the mass flow rate, which gave me this much power, 9 joules per second, which is watts. The rate of the boiler heat in, I calculated using the mass flow rate times the difference in entropy. I got that value. Rate of condenser heat out, I got that value, which is pretty close, which that's actually what makes for the bad efficiency, is there's a lot of heat in and then there's a lot of wasted heat that's escaping through the condenser. So that leads for bad efficiency. Rate of turbine workout, we got was that value, and turbine efficiency, 26.7%. The whole cycle efficiency, because of the high heat escaping from it, I only got about 3.36%. So uncertainty, we had 3 things that we were uncertain about, which is the uncertainty of the temperature measurements, which were about plus or minus 5%. The uncertainty of the pressure measurements, which I think was about plus or minus 5%. And mass flow rate, we were also uncertain about, which was plus or minus 10%. So I just did the square root thing that we learned in instrumentation measurement. We got about that much uncertainty. The turbine efficiency seems low at 3% because typical turbine efficiencies are between 20 and 60%. I looked up the typical values on Google, and none of them seem to be as low as 3%. So, although most of the values seem reasonable because there's so much heat escaping and heat in, either we calculated something wrong or this turbine is just very inefficient. So the conclusion for me is that it's more efficient to have large turbines over at a power plant that actually creates the power, as opposed to having electrical lines actually get the power to your houses and buildings, as opposed to have steam lines come from somewhere else and then have little tiny turbines to power everything. So it's not quite so efficient, but I think it would be practical if you had like a natural gas line or an oil line or something where you have that pressure that's driving anyway, and you don't want to send a remote electrical line somewhere. You can actually just use a turbine to create electricity along the pipeline, or maybe, you know, for an experiment or something like that, it's not so bad. Or in remote locations where you don't really have a power grid, I guess, you know, if you want electricity, it might be good to have a wood power plant or something like that. And are there any questions about this experiment? Thanks so much.